Hi, this is Chapter 5, Section 3, and we're looking at bisectors and triangles, and that's going to be angle bisectors and perpendicular bisectors. So, if three or more lines intersect at a single point, they are called concurrent, and the intersection point of those concurrent lines is called the point of concurrency. And we're going to be looking at in the next two sections are the 4 points of concurrency for a triangle. So our first thing we're going to look at is the concurrency of perpendicular bisectors theorem. It says the point of concurrency of the perpendicular bisectors of the sides of a triangle is equidistant from the vertices of the triangle. Again, each side of the triangle is a segment, and every segment has a perpendicular bisector. So in this picture, you can see these 3 lines are the perpendicular bisectors. Let's go ahead and mark them. They're marked perpendicular, but they weren't marked as bisectors. And then this point H, we're going to call that the circumcenter. It's the point of concurrency, the point where the perpendicular bisectors meet. And that circumcenter will be the center of the circle that will be circumscribed about the triangle. So let's go ahead and highlight that. And let's go ahead and make a note here that H is the circumcenter in this picture above. Okay, that's it for the information on page 1. We're going to move on to page 2. On page 1, we mentioned that the circle was circumscribed about the polygon. And here you just have some examples of polygons where the circle has been circumscribed around the polygon. We could also say another way to describe this is the polygon is inscribed in the circle. All the vertices are sitting on the circle. So again, these are just examples of that. Now, down here at the bottom of page 2, I've drawn the same triangle from page 1. Let me go ahead and show you again. Here's the same triangle from page 1, maybe a little bit bigger. And I've removed the perpendicular bisectors, and I've just left the radii, which are the segments going from the circumcenter out to the vertices. Let's go ahead and draw one here. I'll use the red pen. And so since this point is equidistant from the vertices, you should be using a ruler, unlike me, that becomes the radius of the circle. And so we can see on page 2 the 3 radii. Of course, there's infinite radii, but the 3 that go out to the vertices have been drawn, and then the circle has been drawn around that triangle. So this circle is circumscribed about triangle ABC. Okay, we're going to move on to page, actually let's mark this while we're here. Let's mark these guys equal. Let's make a note on the side that segments HB, HA, and HC are all radii. Okay, it's mentioned up here, but it's good to have a bigger note that you can see. So let's move on to page 3. Okay, on page 3, we have some pictures of different types of triangles and the circumcenter in each of those triangles. So, depending on the type of triangle, the location of the circumcenter changes. It can be in, on, or outside the triangle. So, in the 3 pictures we have below, you can see in the acute triangle, your circumcenter is inside the triangle. For the obtuse triangle, the circumcenter is located outside of the triangle. Again, the circumcenter being where the perpendicular bisectors meet. And then you can see for the right triangle, the circumcenter actually falls on the triangle. It sits on the hypotenuse of the right triangle, and in fact, the circumcenter for the right triangle is at, anybody care to guess where it's located at on the hypotenuse? Well, if you guessed it, you are correct. It is at the midpoint of the hypotenuse, which is kind of nice because you won't necessarily have to go through some really extensive constructions to create the circumcenter. You could do a simple construction just to locate the midpoint of the hypotenuse and be able to draw it. Okay, we are moving on to page 4. Hi, we're on page 4 of chapter 5, section 3, and we're looking at the concurrency of angle bisectors theorem. So, if the bisectors of the angles of a triangle are drawn, they are concurrent, and that point where they are concurrent is equidistant from the sides of the triangle. So right now in this picture we can't see that distance. The point of concurrency is called the incenter, and so in this picture point R is the incenter of triangle MLN. Meaning that the distance from R to MN will equal the distance from R to LN will equal the distance from R to LM. All those distances will be the same, but again, we can't see them in the picture. Since the incenter is the center of the circle that's inscribed in the triangle, that's an important definition. Let's go ahead and orange that one also. In order to get the radius of that inscribed circle, you will end up having to construct these perpendicular segments. And if you take a look, in the picture here, the angle bisectors are now these dashed lines, and these highlighted segments here, these perpendicular ones, those are actually the distances from R to the sides, and those segments, each of them is a radius of the inscribed circle that we have here in the picture. So it's going to take construction to make this, and we'll see that construction in another video. So let us move on to page 5. Okay, we're here on page 5, and now we have the examples for this information. So the first thing it's asking you to do is name the incenter in each picture. Remember, the incenter is where the angle bisectors meet. So if we take a look at the first picture, and it's kind of hard to tell, we can easily see that AG is an angle bisector. It's a little harder to tell here. It looks to me that BD is the angle bisector, and if BD is the angle bisector, we can see that BD meets AG here at point H. Okay, so H is the incenter for that picture. If we go on to picture B, this one's a little easier to see. Why don't you go ahead, stop the video, and take a guess at what the incenter is. Okay, hopefully you stopped the video and actually thought about, I'm looking for the place where the angle bisectors meet. The angle bisectors are NQ and OR, and they are meeting at point P. In the third picture, the angle bisectors are MO and QS, and they are meeting at point N. As you can see here, they've drawn other things to try to confuse you. Okay, in picture D, the angle bisectors here are AE and FB, and AE and FB meet at this point right here, which I believe in the picture is called point I. Okay, for the last example on the page, we're finding the coordinates of the circumcenter of this triangle. Well, because this triangle is a right triangle, we know that the circumcenter is at the midpoint of the hypotenuse. So I'm going to go ahead and find the midpoint of the hypotenuse. Our hypotenuse has coordinates 1, 3, mixed up my x's and my y's, and this point is 6, 1. So to calculate a midpoint, if you recall, to get the x coordinate, you take your x's and you average them. So that would be x1 plus x2 divided by 2, which is 7/2. To get the y coordinate, you average your y's, which would be 3 plus 1 divided by 2, and that leads to 2. And so let's double check that I've labeled this correctly. 1, 3, 6, 1. Oh, yes, I did do this correctly. Sorry about that. I was going to confuse my coordinates. So my midpoint turns out to be 7/2, 2. And if that's my midpoint, then that's also the circumcenter of my triangle. Okay, we are going to stop this video right here, and we will pick up on these examples in class. Right now, you're going to want to go to the construction video for 5-3. Thanks, bye.